Good morning, dear students. In the fifth paper of your MSc Final Physics, I have been teaching you about the energy band theory, and in this particular chapter, we have understood the block theorem. I defined block function, and then I used the same in the Cronin-Penny model, and we came to know that how energy bands are formed when the periodic potential is considered as a special type of periodic. And then in the last lecture I told you about the velocity of an electron in any band. Dear students, whenever an electron moves in a band, then at near the zone boundaries its mass changes in a specific manner, and there we define its mass as effective mass of the electron, and its value is obtained in terms of the double derivative or single derivative of energy with respect to the vector k that I will tell today. So we all are familiar that velocity of an electron in any energy band is given by velocity equals to 1 upon h cross d by dk. Last time I told you that E is equal to h cross k, and that is actually momentum. So if I differentiate, I will get d by dk, or momentum is equal to mass into velocity. So using that particular concept, I can write down V equals to 1 upon h cross dE by dk. Now, if we consider the force F and then the power or energy gained per second by the electron in any field in the zone will be given by this E represents here energy, so it will be the energy gained in the electron will be simply force into velocity. We know it is power multiplied by time, and we all know rate of doing work is defined as power, so I can say dE upon dt would have been power, that is F dot V. So energy gained in an interval of time dt will be force multiplied by velocity multiplied by dt, or F dot V, as I was telling you, d by dt, and d by dt can be written as d by dk into dk by dt, and d by dk we can write down the value from here, that is F will be 1 upon V dE by dk into dk by dt. And what is 1 upon V d by dk? From this equation first it will be h cross, so I shall get h cross here dk by dt. This is one formula for the force. Now again from this first equation, dV upon dt, that is the rate of change of velocity, will be 1 upon h cross and that is 1 upon h cross d by dt of dE by dk, and that is, here I should write 1 upon h cross d by dt of this dE by dk. This is what I have written here, and then it will be 1 upon h cross double derivative of E with respect to k into dk by dt. That can be easily written as 1 upon h cross d by dk dE by dk into dk upon dt. This will be the double differentiation, and I will write like this. Now it is very simple to understand that 1 upon h cross double derivative of d square that is energy with respect to k, and this dk by dt I can write down from here second equation, that is f upon h cross. So I have written f upon h cross. So this equation can be written as f upon h cross square upon double derivative of e. This is dv by dt we are calculating, that is acceleration, and we know by Newton's law that acceleration is force upon mass. So if I compare this equation with a equals to a acceleration equal to f upon mass, then dear students, this quantity, that is h cross square upon double derivative of e with respect to k, is dimensionally equal to mass m, and it is defined as the effective mass of electron in a band. Come to a point here. So I will write this quantity as m star. So dv by dt can be written as force upon mass star, where mass star m star is h cross square upon double derivative of e with respect to k. And this quantity double derivative of e with respect to k changes from point to point in the band. So I can say this is effective mass of electron, and we can draw all these parameters with respect to each other. I have been telling you that if I go for a curve between e and k, the curve is like this. You can see this curve is, and then it starts, the rate of change is first increasing, attains maximum here. As a student, being a student of MSc, I would like to tell you that the slope is increasing, so d by dk will increase up to this point, and then it will start falling, and if the curve becomes almost flat, it will become 0. This is what dE by dk has been plotted. See, it is increasing first up to here, the value k0, and then it starts falling. You can see it becomes 0 at this point. This is d by dk, and as I told by equation first, d by dk is related to velocity, so that's why I have written here v versus k graph. Now if I further differentiate it, you can see that the double derivative looks like this. When it is maximum, it is 0, because whenever a function gets maximum, its first derivative goes to 0. So that of v, it will be 0, the differentiation. And this is a curve showing the acceleration. And if I see double derivative of e is positive in this region and negative, so if I put here, mass will be positive in the first 0 to k0 value, then it will become negative. This is what I plotted the mass. Wherever the d square e by dk square becomes 0, mass goes to infinity. Here negative infinity, here be positive infinity. This is the variation of effective mass with respect to k in an energy band. See, this is negative and positive effective mass. Whatever I have told you by this curve, this is written in my text. I will send you the PDF. So those points where double differentiation becomes 0, the effective mass goes to infinity, and that region in which it is negative, the effective mass is negative, and otherwise it is positive. This is what we have to learn. Our main emphasis in the next lecture will be that what is the origin of this negative effective mass, because we all know in normal mechanics mass is always positive for all particles. What is the significance, physical significance of this negative mass, I will tell you in the next chapter, next lecture. We will discuss all these points and we will define few more parameters. Thank you.